Hello, 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 testing. Hello. Okay. So today we'll continue with proving Tikhonov theorem. So Tikhonov theorem says that a product of topological spaces is compact if and only if every factor is compact. But actually, we proved this kind of theorem for finite product space. Okay, but this proof will work for infinite product case as well. Okay. So there's one direction is easy. What do you think? Eric, what do you think? Forward. Okay, so how do you go from a product space to one of the space? There's an obvious map you can do, right? Yeah, projection. Okay, so we know that the projection is continuous, right? So consider projection map from let's say we call it X. the SJ component. Okay, so this is the projection map. Okay, since the projection map is continuous, so xi being the image of pi of the projection map is also compact. Okay, continuous image of a compact set is compact. Okay, how about the other direction? So you need to use the fact that you know that every factor is compact and then show that the product space is compact. So this is the place where we need to use the Alexandra subspace theorem that we proved last time. So Alexander subspace theorem, what's the thing? What's the statement? Okay, Jingsen, what does the Alexander subspace tell us? 啊，去找啊，刚刚讲没有用，不知道没有用啊，要去找啊，要做工啊，是不是？很多人告诉我这个不会，那个不会，这个不会，问题是他都没有做，怎么会？对不对？你要去做工啊，要去读啊。没有人天生生下来就会啊。有看过人天生接下来会写 ABC 吗？知道吗？嗯嗯嗯，every cover what? Every cover by a subspaces has a finite subcover. Okay. You know what this means? Yeah. So what does it mean in your own word? Huh? Mm, uh-huh. And then open subcover. Finite. Huh? Finite is important here. So compactness, how do you check the finiteness? You check for all open cover, but Alexander's subspace tells you that it's enough to just check on open cover of sub by subbases. Okay, you don't need to check all the open cover. You just need to check open cover by subbases is enough. Okay, so this is what we're gonna use here. So for the other direction, let's assume each space is compact. Okay, again, let S denote the product space. Okay, so we're gonna find a subbasis for X here. Okay, still remember how we construct the product topology. How do we construct the product topology? Exactly using the subspace construction here, where we look at the pre-image of open set in uh, in uh, each xi here. Okay. Okay, so if you still remember the topology we take on the product topology, right? We only have finitely many spot is a proper open set. For the rest should be the whole space. Okay, and then this is exactly what subbases give you. Union of finite intersection. Okay, correct or not? What's the, for example, that one fix this I to be 1, right? So what's the tree image of U here? You have a U at the first spot, and then S2, S3, S4, and the rest. Okay, because this is a projection map. Okay. All right. So, suppose our script A is an open cover of X by subbasis from X. Okay. So, for each I in X, we will let AI to be U in Ti such that pi inverse U is in, I think this is script A. Okay. So what do we do here? So we have a script A, an open cover using this subbasis here. Then we collect these I such that we know that where this pi inverse U come from. Does that make sense? So this script A here is consists of these pi inverse U, right? And then we just collect and classify the U together based on where we pick the pick which topological space we pick from. Okay, make sense? Okay, no. Okay, okay. Then what we're gonna show is next. We show that A must exist an I in I. Let's call it I naught, such that A I naught covers X I naught. Okay, so what does this mean here? This means here one AI is already enough to cover everyone. Okay, one of the AI is enough to cover everyone. Okay, then only then we can use that this topology is compact, and this set can have a finite subcover. Then you can cover everyone else. Make sense? Okay. First of all, we use open cover from subbasis set. Then we just focus on look at each U, okay, coming from one of the TI. Then we claim that one of the AI here is already enough to cover. There's this sum, okay, I naught, that's already enough to cover my whole space, the product space. But not that this U here come from the same topological space. Okay. Then you will have a finiteness coming from the assumption on X. Okay, so we'll prove by contradiction here. So meaning actually we don't know how to find this I naught, but it should exist. Okay, we don't know how to find it, but it should exist. So otherwise, let's say we cannot find it. So for OI in I, there exists some point in the XI not covered by this AI. Okay, okay, before that, so this I naught here is covering some XI naught. It's not the whole space. Just now there's is info. Okay, so one of the I naught should cover the whole XI naught. So let's say that some XI naught is not covered. I mean, for every I, right, there's this some AI, some point in XI is not covered by this AI. All right. Since this is true for all AI, right, then there's a collection of AI that living in the product space is actually not covered by script A. Okay, so this contradicting script A is a cover of X. Okay, if you cannot find I naught such that AI cover X I naught, then you have a sequence, you have a collection of AI such that it is a point in the product space that cannot be covered by the script A. Okay. Okay. So now let's say we can cover Xi naught using AI naught. Okay. Then in this case here, we know that Xi naught is compact. Then we can reduce this to a finite cover. Finite subcover. Okay, the claim here is I can hook up the finite subcover for the product space using this finite cover for Xi naught. How? What do you think? So I think your idea should be like, let's say this is X1, X2, X3, X4, right? Okay. Then we know that, or let's say this one we can cover by finitely many cover already. How do you make this into a cover for everyone? Still using the magic map, right? The magic map. How to go from one set to product space. We know how to go from product space to one set, right? Projection, right? Then how to go backward? Inverse, but not the inverse map, but it's the inverse image. Okay, so then the collection pi inverse I naught x1 u1 up to pi inverse I naught inverse un. Okay, should live inside script A. Okay, so this is a finite subcover of X from. Okay, this element should live inside my script A, right? I think because pi inverse of these UI is something inside A. Okay, so they should come from A. Basically, is this, but I think yeah, basically is like this. Okay, does it make sense? Okay, so if you imagine visually, what happened just now was we have some open cover like this, like this, like this, like this, right? Okay, but the claim is there's one set of things that can cover the whole component. Okay, and then we use the components of this component to reduce it to a finite cover here, and then I use inverse map, straight away cover everything else. Okay, make sense? Okay. Any question before we go to the next section? So this is about, what is this about? Tikhonov theorem. So why we reach Tikhonov theorem? What's this section about? What's this section about? Why suddenly we reach Tikhonov theorem? What's the thing before Tikhonov theorem? Huh? Oh, metrization. Okay, metrization. Oh, okay, sure. Okay. Ah, right. Compactness. Yeah, okay. So I think this is counted as a starting of a new section. So we got what next thing we're gonna do is called a stone check compactification. the stone check compactification. Okay, so previously we talked about metrization, right? When can we give a metric to a topological space? Now is how to make a non-compact space compact, and how to make a compact space compact. So actually we touched on this once, right? Where we talk about the one-point compactification. Okay, if you still remember, a very important example in one-point compactification is if you have a line, real line, right? I add in an infinity, what you get is a circle. Okay, this is very important idea. And this is what we will coin as a, or call it as a minimal compactification. It's minimal. Okay, there's only one point you need to add it in. But later we will introduce something called a stone check compactification. We will term it as a maximal compactification. Okay, so this is a maximal thing you can do. Okay, to compactify it. I hope later we will justify better what does maximum mean. Okay. All right. So let's give a definition first. So we say that a compactification of a space X, okay, is actually a compact Hausdorff space, okay, which contain X as a subspace, such that if you take the closure of X, you get Y. So what's the compactification of X means? Meaning it is another space which is compact. Obviously, we want it to be compact. Secondly, we want it to be Hausdorff as well. So very nice property, huh? So, 它是个动词还是个名词？它是个名词 right? Compactification 名词 right? Yeah, 名词。Compactify then is a 动词。So if you compactify and space X, it's like you go and find the compactification of X. Correct. Make sense? Okay. So compactification is a noun, right? Of space. 这个 space 的 compactification. Yeah. Okay. So 这个 space 的 compactification 是另外一个 space. Okay. What is this space? Is a compact Hausdorff space. Okay. Make sense? Okay. Such that the closure of X is Y. Closure. Okay. So meaning you add in the limit point. And then we will say that two compactification y1 and y2 of X are equivalent. Okay. So in topology, right, two spaces are equivalent. What do you think? What kind of bijection we need to put it in topology? What kind of bijection we care in topology? Homeomorphism. Why homeomorphism? We want to preserve the topology. Okay, inverse open set in one space is open in the other space as well. Okay, under this map. So if there's a homeomorphism. In group theory, you care about what? Homomorphism or isomorphism, right? In linear algebra, what do you care about? Also called homoiso, or more precisely called a linear transformation, right? Yeah, linear transformation. Okay, so can you remember compact Hausdorff space? Okay. So there's a remark I want to say here. So compact Hausdorff space is normal. Okay, is normal. So by Arista lemma, right, y is also completely regular. Okay, you can use function to separate. So being a subspace of the completely regular space y, right, x is also completely regular because we say that completely regular is a hereditary property. So you can pass on to your subspace. In fact, the other direction is also true. Okay, so if X is a completely regular, then X has a compactification through the embedding in a compact Hausdorff space. Okay, this is what we did in in what in the proof of Arison metrization theorem. Still remember or not? What's the proof of the Arison metrization? We use a countable many function to represent our set inside an infinite product space. Do you remember? Okay, so later we're also gonna use this technique to compactify our set. Okay, actually the subspace we land inside the product infinite product space, right, is actually a compact Hausdorff space. Okay, actually we say that it just land inside a subspace, right? That subspace actually is infinite product of 0 to 1 space, because that function only can how do we construct the function? I still remember or not? On one set it takes 0, right? On the other set it takes 1, and then you fill it in using a recent. Okay, so actually you land inside a closed interval from 0 to 1, infinite product of closed interval 0 to 1, which is a complex Hausdorff space. OK，懂我讲什么吗？对吗？OK，所以上次我们只是 land 在一个 subspace of 一个 R 的 infinity，那个 subspace 其实是一个 infinite product of closed interval from 0 to 1，因为我们的 function 只能够 evaluate on one set is 0, on the other set is 1. And then 我们用 Arison lemma 来把它填完 continuously. Yeah. So actually you really land inside a compact Hausdorff space. Okay. So we're gonna use this kind of construction to build our strong check compactification. Okay. So here's the lemma. Here's the lemma. Let's consider topological space. Okay. Suppose that H from X to Z is an embedding. Okay, still remember what embedding is? Embedding. Think of yourself embed in this classroom. How is it embedded? Let's say our Z is a Hausdorff space. How is it embedded? Embedding. What are the property you need? Injection. Okay, it's an injection. And then it's an homeomorphism onto the image. Okay. Obviously, if it is onto the image, it's surjective. So another thing we want it to hold true is it is a homeomorphism. So topology is preserved on both sides under this map on the image. So it's embedding, embed inside here. Then there exists a corresponding compactification. So it's a space, compactification of a space is another space. Okay, let's call it X. Sorry, Y. What the property it has here? So it has the property that there exists another embedding. Okay, from Y to Z that equals H on X. And we will say that or prove that or claim that this compactification is actually uniquely determined up to equivalence. Okay, so actually this kind of this configuration actually is unique. Okay, this is what you want to say. And then we will call that Y is the compactification induced by this embedding here. Okay, so what can you imagine here? So if I have the same X and Z, right? If I change H, then your compactification would change as well. Okay, because this is really depending on this embedding here. Okay, depend on how you sit inside here, then your compactification is different. 对吗？招生是不是？You behave like this in my class, you behave in the other way in the other class. Then the teacher see you as a different people. Although you are the same X, right? Okay. Okay, so depend on your theta H here. Although X and Z is the same. Okay. Right. Let me see. Let's see. Can I draw this diagram out? So let's say I have X to Z with this embedding, right? Okay. And then we have a compactification of Y. So there's another embedding, right? So embed it into X. So this is compactification such that there exists another embedding, okay, Y into Z. And this is a H. And then equal to H on X. So let's say this embedding is G. Okay, so then we'll get H composed G equals to little H. Okay, this is applied on X. Okay, makes sense? So you could think of this compactification here is like something before this compact Pascal space. It could be Z, but could be something smaller than Z or bigger. Smaller, need to be smaller because this is an embedding. Okay, actually it's an embedding. So there are three embedding here. Okay, we will do a proof sketch here. We won't write down the whole proof. You can see from a Moncrief's lemma 38.1. Okay, so let's see how we're gonna do this construction here. So what do we need to do here? We need to find Y. Okay, we need to find Y, and then we want to find capital H. Right, this is the thing we need to do here. Okay, because this is an existent statement, right? So the exists here, and then the exists here, and then we need to check this. Check compactification, check this restriction property. Okay, because there are a few things we need to do, so that's why we're not gonna check it very detailed. But I will tell you the idea so that you can understand what the test book is doing. Okay, so first of all, so you can keep this picture in your mind. Okay, this picture in your mind. Okay, we want to find Y. So what we want to find Y, find H. Okay. Okay, so well, let's see what we have now. So let's denote S naught to be the homeomorphic image. Okay. This is how X sit inside S naught here. Okay. Right. So let's say X is like this. Maybe use different color. So maybe X is like this. And then Z is something else. Okay, I want to see how X sit inside Z here. Okay. And then next thing we're gonna do is before finding Y, okay, what we're gonna do is we set Y naught first. So let's say we close Hx first. Okay, close it. And look at the closure of this topological space. Okay. So in this case, right, what can you talk about why not here? It is closed inside a compact hostile space. Can you talk something about this subset here? This closed subset here being inside a compact hostile space. Closed in compact is what? Close, not just close, right? Close is compact is compact. Okay. So first of all, this why not is compact. And obviously Hausdorff because it comes from a Hausdorff space. Okay. But this why not is not yet our why. It's not yet our why. Okay. So let's continue. Uh, it's not yet our why yet. So how do we build this why? Let me see. Something wrong in my knot. Why suddenly there's an A coming up here? Then let me see. What am I doing to do next? Okay. So then this is very mysterious. So let Y be something called X union A. Okay. X union A 不知道什么是 A 现在So like now I'm gonna characterize what A is. This A intercept U should X has to be empty. Okay, so meaning this A is not coming from X. Okay, let's continue. Let's see where should this A come from, such that we have a bijection H from Y to Y naught. Okay, Y naught is something we know. Y is the one we want to build. Okay, such that we have this bijection here. Okay, we don't know what A is. Okay, we want this A such that we have this bijection here. Biject to this Y naught. We don't claim that Y naught is Y, but Y naught is something inside the Z, such that what? Such that X will in the newly built space will get sent to HS, the small HS, if X is coming from X, because remember just now, the big H have to satisfy what? In X, we have to evaluate as HX, okay? And then what's next? We have to send it to something called KA if A is in A. So you see, so my Y, right, is two components. One is X, one is A. So if I build a function from Y, I need to tell you where X go, where A go. Okay. But now I put a K here. So this K is another new thing here. There's a lot of bijection going on here. So this K here is A going from Y naught take away X naught is a bijection. Okay, so this until here makes sense or not? What is Y naught minus X naught? We define X naught to be what? Sorry, define Y naught to be what? The closure of yeah, the closure of X naught. Okay, so exactly what this means here. What does this mean here? Uh boundary point or limit point more precisely. Precisely limit point. Okay, yeah. More precisely limit point. Yeah. For sure it's limit point because we proved that closure can be written as a step plus a limit point. Boundary point. Boundary point also same. No, right. For boundary point, there's another term, is it? What's the term? How to express closure as a boundary point equal to what plus boundary point? Also just X naught? Also two components? Then you can call it boundary point. Oh, yeah. Right, right. Okay, yeah. Another thing that last time we miss out is about boundary point of topological space. We didn't really treat it properly in this course because we don't really have question on that, and also we thought that it's all just generalization from where from metric space. Let me see. I think I write down something. That one is after your lecture, but won't be included in your test. No worry. But for completeness, I think I added in. Right. So here it is. So if you really want to talk about boundary point of a topological space using, sorry, if you want to talk about closure, okay, in terms of a boundary point, right? Actually, it's not A, it's interior of A. Okay. But we can talk about closure of A, okay, using A union limit point of A. Okay, this is true. Make sense? Okay, so if you want to talk about boundary of A, actually you need to talk with interior of A, such that the intersection is empty lah. Okay, this is what we meant here. Make sense? This two intersection is empty. Agree? Interior of A and boundary. Yeah. Okay. So here the union here is a bit like a direct sum or disjoint union. Okay, we want to split it. Either you are in here or in there. Obviously, you can replace with A here, but not very interesting. Okay, because points in A could be in boundary point of A. But the point of this union is a disjoint union. So meaning a point in A bar either here, either here is disjoint actually. Either you are interior, either you are boundary. But just now we want to split it as a either you are limit point, either. Is it? Let me think. Not quite true. Is it true? Seems like there's a intersection between. I think this is not a disjoint. This is not a disjoint set, right? You could be a limit point. You could stay inside A as well. Okay, but the point here is if I take A bar, take away A, it will be a limit point. Okay, right. Okay, where am I? Okay. Right. So where does A come from? Actually, this A actually really come from nowhere. It's just something. Actually come from nowhere. Okay. Actually come from nowhere, this guy. This A here. It's just some other set that I want to edit in. Come from nowhere one. For example, let me ask you last time, right? Like let's say we have a line, we have a point here, and then we say that oh this one will compactify into this, right? But if you ask me, this point come from where? It's not also come from X itself. We are not taking some point here and then put it together. It's just somewhere. Okay, right? So this union here is pretty important. Okay, it's pretty important. Pretty important here. This union here. Um, so on how to glue this, this is what will be precisely done in algebraic topology, but not in this course here. For now, you will just see it as a union. Okay, for now you'll see it as a union. And then we will mention a little bit about the topology. So how is it? Yeah. Okay. So now topology is becoming important here. So if we topologize Y by declaring U to be open in Y, if and only if F U is open in y naught. Okay. So this line here somehow tell you what happened. What happened when close to here, close to this point here, close to A. Okay, somehow this topology tells you how to close to A. Okay, so what? So can you see that X is a subspace of Y because it's a part of the union? Okay, and also hash restrict to X is just little h. Okay, satisfy the condition we want just now. Okay, this embedding, and then because we want to prove compactification, right? We need to prove it is a subspace. And then what else? You need to check. So the hash actually is embedding into Z. Okay. But where we map this into, so Y map into Y not, right? But Y not live inside Z. Okay, so it's embedding into Z. Okay. So now we're gonna prove why is it unique. Okay, why is it unique here? So the proof of uniqueness here is very standard. Okay, so this is a very standard argument you're gonna see in higher maths. It's quite, how to say, I cannot say technical. It's quite standard. Okay, without really knowing what is compact, the real compactification meaning, but just need to play with the two embedding. Okay, so let's say we got two embedding here as an extension of H. Okay, so at the same time, what do we have? H1 Y1 is equals to S naught bar equals to H2 Y2. Okay, do you buy this line? You buy this line or not? Do you buy this line? Or maybe you can quickly write down. So let's say X naught here is live in both of them, right? Okay, obviously this implies that S naught bar should live inside H1 X Y1 because we say that this image here is compact. Okay, so your closure should live inside there as well. And obviously, we know that Hi, Yi are both living inside S naught bar. Okay, this is by construction. Okay, because this is the exactly the Y naught bar. Okay, so what we're gonna do here, to this end. So how many things we have? Let's write down first. Maybe picture look nicer here. So we got Y1 to Z, and then Y2 to Z, H1, H2. And then we want to show that H1, H2 is the same. So what's meaning the same here? Meaning there's an isomorphism between Y1 and Y2. So H1, H2 are embedding, right? Okay. They both embed into Z. But you know more than that, right? Actually, you know more than that. Actually, you know more than that. You know that this Y1, Y2, right, is homeomorphic into something smaller in Z, right? Which is which is S naught bar here. Okay, so how to go between Y1 and Y2? Yeah, use H1, H2 lor. So you can go H1 and then H2 inverse. Okay, take those, use H1 and then H2 inverse. Okay, so let's say you go this direction here. So let's do this direction, H2 inverse on H1. Yeah, so this actually defines an homeomorphism, okay, between Y1 and Y2. Okay, homeomorphism between Y1 and Y2. But note that this homeomorphism, right, is actually an identity on X. Okay, why is that identity on X? So remember, when we restrict H1, H2 on X, right, what are they? They are just little h, the embedding of X. Okay, so they cancel out its X. Okay. Okay. So we'll say that by definition, Y1, Y2 are okay. Okay. So next, the definition is here. Okay. So if equivalent, you have a homeomorphism between Y1 and Y2, and then on X is an identity map. Okay. So this is the two things you need to check. So just now we checked this two things. We got homeomorphism, and then on X one is identity. Okay. So can understand this statement here? Equivalent. So on X, you don't change it. Okay, you should think of this Y1, Y2, right? So let's say X like this, and then maybe Y1, Y2 a bit bigger. Y1, Y2 like that, right? Okay. So on X, there's a homeomorphism between these two. On X, no change. But on other places, maybe you can change a little bit. Okay, homeomorphic. Makes sense? Okay. Then we only say it's equivalent. It's not just homeomorphism on these two spaces, but need to be identity. On X, I don't change. Outside, I can change. Okay. Okay. Any question before we take a break? Any question? So after break, we will see a few examples. We'll look at some small h and then see what kind of compactification we can see from this small h. Okay, let's break for 10 minutes. Let's break until 11:06. 老师，哎，啊，
老师，
哪个？
那个
还没有吧？这样没有给我，
没有给你，
有几个给我？
刚刚他们说12点的，
对呀，
你不也说12点？
对对对，
去打。
什么？
好，
来看一下。满，就一个组啊。
有什么？
哦，这个组满了啊，actually interesting interesting。
这不是刀片了？
你可以 download 是吗？它是 copy paste 在里面，它的照片 copy paste 在里面。它有些如果还没有给照片就算了，不用放；给
这么长的，
有翻了就放。太长没？这个算短吧，应该。
很短。那我写太短了。
不用紧，OK 啊，都 OK 啊，不用紧啊，没有不重要。我是说，如果到最后没有给照片，就不用放照片。
对，
嗯，然后放一个 empty set 给他。
什么给照片？你把我来再默写，为什么？这开头写的好长啊！我操！
不用了，不用不
那
用不用不用，
我先不用
不重要不重要，只要精准讲到你要讲的东西就好。
子谦还没给我照片怎么办？
你提醒他，如果没有就没有。
我先把其他人都上传了。对，
可以啊，
一个组的我放在一个 Word 里面可以吗？
可以要
按顺序，
按顺序来。
按顺序。对，按顺序放在一个 Word 里面可以。
Yeah,
OK，
can you enumerate? 对啊，反正是没有的。他们也会说中文啊。对，咱们不是说电视的吗？聊什么事？哦，可能会是，没关系，就是他会跟我讲话，所以那我会讲话，不开的多，对，OK，是。 出来了，
过了很多天的香槟，
哇哦，从哪来？马六甲，
还有绿色。放在你的有些
有去，
你去过马六甲对不对？
有，我吃过。
你在上面吃
哦，OK，
饭的时候，因为我不想让它放太久，放太久
马蹄酥，
我们是叫香槟，
嗯
我很喜欢它里面那个
嗯，
麦芽糖，
去买。哦，
想跑去了，然后在上课，
嗯，有。
比如 college 今天来，
Supposingly 啊，他没有 contact 我，我给他电话，看了，
改去这个礼拜，
嗯
他们改去这个礼拜来，
嗯，对，你讲对，
嗯，可是 college
嗯，一个人罢了，嗯哼，
很棒，这个怎样讲呢？是我们 application，
嗯
我下面还有什么事情？把你们有联络的这件事。
嗯，
很好。
跟我拍照吧，
因为他们要
他问 uni 吧，
啊，对咯，对，
但是他们比较
有事情。
离开我们，因为比如说他们的 contact 干什么？在跟约就可以了。他比较皮，他们也他可以不能比较皮。
应该是因为他们也不是那种参与我记得讲的参与根本就还有几个 Excel 啊，
有没有他们的自己的程序？
我没有服的，但是我了解都会提到你是另外的书。
你可以跟他打他的那个电话去报，就这样。
可以到，
哎，他女朋友吗？
国立大学，
他在实力不是很多，他是数学，物理，但是我觉得物理应该也还吧。
这里不是这样。
就说这里有些课可能在他们那边有做这吧。
是，
那在国内吧是感觉
对啊，更多，更多，
内地都有过，咋的？比如说有几个
答案还可以啊，但是就是说能不能够有用，有用 for 你啊，step like continue 你的 career。啊，okay. Let's see some example how we compactify using this small h, big h, y, this kind of construction. Okay, let's see some examples. Okay, so first easy example is this. We had consider a small h. Let's call it h1. Later got 3 more. From 0, 1 to s1 here. So what do you think? How do we embed this? I think this is a standard calculus 2 thing. How to embed this? You use trigonometry. So how do you embed? Sine cos. Okay. So cos 2 pi t sine 2 by t. Okay. So you can view this as your x. Okay, so who is your z in this case? Okay, maybe I'll just write it down here. X is 0, 1 here. Who is compact Hausdorff here? What do you think? There are 3 choices for you. x1, x1 is compact Hausdorff, right? Okay. Right, you can show that x1 is compact Hausdorff because you can use every finite cover to. Okay, so maybe let's try it. So your x1 looks like this. Hey, sorry. This is your z. Okay, well, I mean your 0, 1, your 0, 1 looks something like this. Okay, then you have a map, theta h. So you map to this x1, which point you miss? Which point you miss? Which point on the z you miss? What's the point that you miss out? When t equals 0 or t equals to 1, right? What do you get? 0, 1, right? Okay, so actually you miss out 0, 1. Okay, this is the point you miss out. On all the other points, z cross s throw where 0, 1, right? This point here. This is exactly the image of x. Okay, make sense? Let's say if I want to close it, just now I close it, right? I look at the bar of S0, right? Okay, this is what we call S0 just now. Just now y not equal the closure of this, right? So y not at the closure of this is what? What do you think? If I close it, if I close this thing, how I close? Where's the limit point? Exactly this point. I close it, I get the z, which is s1. Okay, so using the construction just now, what should be my y? So basically, this y is x union some a, right? Such that some bijection whole. Okay, so actually there's only one point I want to add it in. Maybe you can just call it a point, but another evidence support that this point we should call it infinity. Another evidence is you need to go to other class. Okay. What? You should learn more max, so that's the reason why we call it infinity. Yeah. Okay, but for now it's just a point. We just added a point here. And then so that we can look at this large hash here. Large hash here is y to y naught, such that on x it is little h. So we still do the same thing. Cos 2 pi x sine 2 pi x. Okay, if x live inside 0, 1 here. But how about if x is this infinity point or just some random point? We send it to where? Zhao Shen, where should I send it to? Yeah, 0, 1. Okay, so then you prove all these are homeomorphism, everything you check. Okay, so this is the construction. Make sense or not? Okay, so we cannot really call this why not. What's the reason? We cannot really call it why not here, right? We cannot really call it why not because this x by right is not something here. It is a space by itself. Okay, and then this point that I add in there, the set of a that I add in there, it's not necessarily the point on Z1 as well. It's just something else. Okay, so that we have a homeomorphism. Okay, make sense? Yeah. Okay. So another example. Let's see another example. Again, we want to embed 0, 1 again. But the way we embed this is a bit trivial. Okay, so what do I mean by trivial here? So let's say we want to embed this 0, 1 into closed interval 0, 1. What do you think? How should I embed it? A very obvious embedding. What should I do? Inclusion. Okay, inclusion, x to x. So if I draw this picture out, it's like this. So 0, 1 like this. Okay, and then we have the whole thing from 0 to 1. Except 2 points. Okay, what's the point? One is 0, one is 1. Okay, so just now we said that, oh, this is x, This is the image of X inside here. Okay, this is a compact Hausdorff space. Agree, how? We spent a long time proof that this is compact. Hausdorff, I think it's obvious. Metric space. But if I look at the closure of this line inside this compact Hausdorff space, what do you get? Where's the limit point? 0 and 1. So this time you don't add 1 point only. You add 2 points. And then you add 2 points. So we see that. So the claim here is actually y, okay, y equals to 0, 1 union. So this time we can call it 0 because it's obvious that we want to add the 0 in and the 1 in to make it 0, 1 is we call that 2-point compactification. Just now it's a 1-point compactification. Now it's a 2-point compactification because we add the 2 limit points. Okay, and this time it's obvious that we know what point we want to add in. Actually, it's a 0 and 1. So we can, it has a proper name. Okay, let's look at 2 more embedding of 0, 1. We can get different picture one. Okay, so let's do the next one. Okay. So the next embedding is hash 3. Okay, from 0, 1 to -1, 1. Okay, you know what's -1, 1 here? Is a box. It's a box. So let's draw the box. -1, 1, and then yeah. So sorry. What am I doing here? Oh, right. Okay. So I should put the coordinate. So here is -1, -1. Here is 1, -1. And then here is -1, 1. And then the other side is 1, 1. Okay. So how am I gonna embed this? You cannot guess this time. Okay, you cannot guess because I can do anything. So X go to this topological sine curve here. Okay, still remember this topological sine curve here. So let's draw this graph like this. This. Right. So you should start somewhere around here, and then you oscillate, getting more frequently, and you reach the y-axis. Okay, still remember this picture? Okay. For this open interval, right, 变成一个线。有没有缝过衣服啊？有会缝衣服吗？You don't, I think. Yeah. 然后你没有缝啊，你剪了丢在那边，那绳子是不是变这样子。Okay. So now in this case here, what is the closure of this image under there? We discussed about the closure, right? The limit point of this. What's the limit point? What's the thing we need to add into? 0? You mean this 0? 0? Not enough, because if I go to this point, I make a ball here, I still can intersect this line infinitely many of them. So actually, it's the whole line from the whole interval 0 to 1 on the lines. And so you need to add this into it. Okay, so the closure. So why? So we will say that this compactification here is isomorphic to the closure of 0, 1. Okay, which is equals to x cross sine 1 over x. Okay, maybe don't use cross, use this, such that x is in 0, 1. And then union 0 y to y for y in -1 to 1. Okay, we add in this line here. Actually, there's one point you need to add in, which is this point. Okay, why we need to add in this point? Is this point defined or not? Is it defined here? No, right? Because we throw this point is defined by x equals to 1, right? But there's no x equals to 1 here. So apart from adding this line here, we have to add this dot here as well. Yes, this extra dot is not defined as the image of 0, 1. So this image here is 1 sine 1. Okay. Okay, so you add in a line add in an interval plus a dot plus a point. Just now I add 1 point, I add 2 point, now add 1 point plus a line. Okay. So this example is precisely saying that this function is not continuous. You see, if you want to add the limit in, wow, so many limits you need to add in. Cannot work. This failed the vertical test, not a function. But in topology, we can do that. We take the closure of this graph. Okay. Make sense? Okay. So now this one is compact. So this whole thing here is compact now. Okay. Last one before we go to the next one. Again, 0, 1. Okay. This one a bit related to your calculus 2. So let's map 0, 1. This time is a half closed interval, not open interval. But we know that this is homeomorphic to 1 to infinity. Okay, just do some scaling here. Then we will do map on this guy, embedding on this guy. So we see it as a polar coordinate. Yeah, polar coordinate, and then send it to 1 minus 1 over theta. Anyone know what this picture is? 1 minus. So theta coming from 1 to infinity, right? Okay. So what are you getting? First point you get is 1. What is 1 here? So how to see this? How to see this map in R2? Is it a point in R2 or 1 minus 1 over theta here? Huh? It's just one number. Okay, so I think what we should get is actually theta comma 1 over 1 minus theta. But this is a radial coordinate. It's not xy. So you need to plot properly. So meaning your radius. So last time we put radius first or theta first? R theta. Okay, let's put like this. This is not xy coordinate. So meaning your angle increases, what happened? Your radius decrease. Okay. Spiral. Okay, it's actually spiraling. Okay, so how it spirals? How does it spiral? Yeah, this is a spiraling stuff. Let me see. When theta is 0, right, what happened? Theta cannot be 0. Okay, good. So, so when theta increases, that 1 minus 1 over theta get really close to 1. Correct or not? When theta increase, 1 over theta become very small. 1 minus very small thing very close to 1. Okay, so how does this start thing to spiral? So let me draw here. Okay. You should start somewhere inside, right? Okay, you start where basically? 1 minus 1 is 0. 0, 1. 0 radius theta 1. Doesn't make sense, right? It's just a 0 point here. Okay. When the theta start increasing from 1, your radius starting to grow. Correct or not? For example, theta equals to 2, 1 minus 1 over 2 is half, and then starting to grow. But when theta get really large, right, you keep turning around, the radius get really close to 1. So there's a 1 here. So it get really close to 1. Can it reach 1 or not? Can reach 1. Let's say 1 is here. Can reach 1? Can reach? Can reach 1. If you take theta, go to peak. Can reach or not? 1000. Can 1 minus 1 over theta reach 1 when theta get large? Yes, man. Tell me which theta again you get 1. No, right? But you get infinitely close to radius 1. Okay, so you are somehow like 被关在这个 1 的 ball 里面. Right? You are inside this sphere with radius 1. So how do you take the closure? Where's the closure? The closure is exactly the circle with radius 1. Okay? Yeah. Okay, huh? Yeah. So this is your compactification inside R2. Did I break the rule? Is R2 compact Hausdorff? R2 is not a compact Hausdorff. So what should I consider smaller here? Can I consider a smaller set here? Close this. Okay, let's consider close this here. Bottom or top? I think bottom. And 0. What's my notation again? Too many notation I forgot already. Did I put radius in subscript? And then center in the middle, like that. Okay. Okay. So that one is a compact Hausdorff, your Z. This is your Z. Okay. All right. So far, okay. So these are different compactification of space. Okay. So next question we want to ask about. If Y is a compactification of X. Okay, let's say if Y is a compactification of X, under what condition? Okay. Under what condition can a continuous real value function f defined on X can be extended continuously to Y? Okay, this is a natural question you will ask, right? Because from X to Y is just adding limit point. Then if you have function on X, can I also define value on this limit point such that the new function is continuous? There's one thing you cannot do, right? This thing here. This fell last time. Topological sine curve fell. But in general, can we do that or not? Okay, or if we can do that, under what condition we can do it? Okay. So partial answer to this is the function f will have to be at least bounded. Need to be bounded if it is to be extendable. Okay, why? Because its extension will carry the compact So why? Because the extension will carry the compact space Y into R. And so it should be bounded. Okay, because last time you see that function on compact space will achieve maximum minimum, right? Okay. But actually a boundedness is not enough. Okay, but in general, boundedness is not enough. But at least need to be bounded. Yes. Huh? Then you need to check whether your function is continuous or not. Later not continuous. Correct. Yeah, you need to check continuity. Yeah. The point here is we want to extend continuous function to continuous function. Obviously, if I want to send point, I just randomly send, but I want it to be continuous as well. Yeah. Okay, you can define a function, but I want it to be continuous. Okay, so let's give some example. Let x to be 0, 1, and x 1 point compactification, which is x1. This is a bit related to functional analysis. So you see, let's say I got a function. Let's say, okay, maybe we see it as one of them is R2, one of them is in. Okay, both of them in R2 actually, for easy demonstrating. Or is it easy? Okay, maybe. Okay. Wait, let me set up my thing first. Okay, how about I made the y-axis in this color? And then x-axis in this, the codomain axis using purple. So let's say your space is from 0 to 1. Okay, I have a continuous function here. Like that. Can I extend this continuous function to a function of circle? 大家来看一下这个东西很好玩，来看一下这东西很好玩，来看一下大家。So 我有一个 continuous function define on 0 to 1 something like that 随便。Okay, but now 我要 extend 去这个 x1 上面Still remember how to make this 0, 1 to x1 我把它转一圈嘛，对不对？我转在哪里呢？我转在这个 x1 上面嘛，但是少了什么？少了这个点0, 1 yeah good。所以我也可以，我当然也可以绕这条蛇在这一圈上面嘛，对不对？something like that 对吗？我也可以绕在上面，把什么时候我可以跟它接起来？什么时候我可以跟它接起来来，我绕一圈什么时候我可以跟它接起来？假设这一个是这一个零的 graph， 这是1的 graph 这边，我绕一圈回来了接得起来吗？这样子 ？Yes, left and right limit have to be the same， 我才补回来这个洞不然我要补整条线呢。我可以补整条线吗？不可以不是 ？Okay, so so we will make a statement claim here. A bounded continuous function f from 0, 1 to r is extendable. So let me draw something here. Or maybe like this. Ooh, like that. Or here, top, here, bottom. Is extendable to y if and only if the left limit and the right limit on 0, 1 have to be the same. Okay. So a function on a circle actually is not, how to say, not strange to people. Why? Because in this world, right, a lot of things is periodic. A lot of things is periodic. If you study what happens. For example, COVID-19 is periodic, you know. Like 100年前也有这样的事情发生过。I mean 不是 COVID-19 but 就是一个很大的疾病。200年前又有发生过，好像每100年都要发生一件这样的事情。Okay, something like that. Okay, so it's not so this is one way to do it left and right limit. Okay, how about the other case? Let's say the closed interval 0, 1 is the 2 point compactification of x. Okay, so in this case, let's see on this case then. So let's say we have 0 to 1. Okay, I have a continuous function. Right. How do I extend to the full interval, closed interval? How do I extend? Can I extend or not this time? How do I extend? If I have a function from 0 to 1, to extend the point 0 and 1. How to extend? Can I simply add point here? Can I add here? Not continuous. Add here, not continuous. So what point I should add? I already give you hint, right? Draw the circle already. Limit point, no? Okay. So the claim here is f is extendable. Extendable meaning I want continuous again, not just function. If and only if both these limit point exist. Exist, then you add it in. Okay. There's no left-right limit to check, right? Because you are already reached out the boundary point. There's no left-right to check. Okay, previously you check continuity, you need to check left-right. But here is already boundary point. Okay, as long as the limit exists, then we add it in. Okay. So no need equal or what. Just fill it in. Just fill the limit in. Okay. Next. What time is it? 1135. Okay. Okay, next, what should we do here? Okay, next one, we do the topological sine curve. Very interesting. So let's see if we can do it or not. So let's look at the case of fx equals to sine of x. Okay. So let's consider the embedding h from 0 to 1 to -1, 1. Okay, x ascending to x, comma x, y, y. Okay. Hey, what am I doing here? Okay, good. Okay, so now we're gonna find extension of fx equals to sine 1 over x. I want to find this extension. Okay. But not that this x, where is the domain? 0 to 1. Okay. But the 0 to 1 here, we want to complete in here. 很变态哦，我觉得这个，我觉得这个蛮变态的。为什么变态呢？因为 somehow we are using the graph of f to extend it。哪里解错？什么解错？什么 ？x 什么 ？cannot be zero。这个是这样子。OK。Okay. So in this case, we will let h be the embedding of y r2, and that equals small h on x. Okay. So now the x we consider now is this one, 0 to 1, and then our y is something homeomorphic to x, x hash x bar. Okay, something homeomorphic to hash x bar. Okay, and then we have this map here. Y is embedded into h. Okay, do you remember the picture just now we draw? So let's say we have like this, and then we have topological sine curve like this, right? And then we complete it. So we complete like this, like this, like this, right? Okay, this is my y. So this is y sitting in R2. Okay, so h embed this y here. So to be precise, I need to say hy like this. Okay, which is isomorphic to y if you like. Okay, this is the whole picture. Then I can project it to the second component here. Okay, which is this value here. Okay, so let's see. We claim that this is an extension of f. Where we claim that this is an extension of f. Okay. 变态吗？你觉得？变态吗？ So just now previously we got 0, 1, okay, and then we map it to sine of can we write like this? Wait, let me see. So 0, 1 map to r, right? 0, 1 map all the way to r. Okay, wait. Okay, so let me write in here. Oh, okay, actually I got things. So previously we got 0, 1 map all the way to r by doing x2 sine 1 over x. Okay, but we claim that after we compactify this 0, 1 inside that space, I obviously need to tell you where these things go. Okay, where these things go. But these things go by this h. Maybe it's not like a sine function governing anymore. It's this bijection here. 有点像刚才李迪亚讲，我就是把它送去这个点吧，把它送去这个点。Okay. So that this whole thing is closed. And then 我再把它送回它的 y coordinate。可以想象发生什么事情？Yeah. Sorry. Remind you about what? Choice function. Okay. I have no comment, but 你可以想一下，我真的没有 comment。你想一下，你可以想一下，我没有 comment。你想一下，我包对也包错，但是我现在要讲的是 ，what I want to say is now。你看，刚才我不是跟你讲有 vertical line test 的 problem 吗？为什么现在没有 vertical line test 的 problem 啊？问我 ，because my y already live inside r cross r. So meaning what? This line is already a point in R2. It's no longer real line. You understand what I say? So this 0, 1 because your 0, 1 like start here, right? Okay, 0, 1 start here, right? So every point here already gets sent to somewhere here already. So let's say this one is S0, Y0, and then this one is S0.1, Y0.1. But then what this map is doing here is just read out the Y coordinate for this point. This point is different already. Even on this line, right? The coordinate is all different. So we treat them as different point already. But in this one-dimensional case, 好像蚂蚁这样, you cannot see these 2 points. 你只是一条路走过，你不知道你是在 R2 上面，你是走一条路了。Okay, so after this embedding, right, this R point here become an R cross R point. 你看每一个时间点 ，you can think of it as a timeline 每一个时间点 you have a point in R2, yeah, to go to position. Okay, so this extension here actually works on R cross R actually. Okay, so 你把一个 one-dimensional a function of a real value extend a function of a two variable, function on one variable extend function of two variable. Make sense? Just now 我们只是加那这个 y 点嘛，但是现在你连你的 domain 都变掉。Okay, make sense 啊？ So there's a hack here. 有一个 hack 在里面。Okay, although 是 R2， 但是 most of the point I can parameterize it， 对吗 ？Parameterize 用这个吧，其实是一条线。But there's some place I cannot parameterize properly with 这个里面的东西。So 这个 this compactification provide me a hack. This embedding provide me a hack to tell me what are these points I need, and then what I can do to those points. And then what's the function you get here? Actually, it's just a projection. It's a homeomorphism plus a projection on it. Project. I read the y coordinate. That's it. Okay, but this doesn't how to say, doesn't contradict with the vertical line test, because we treat all these points as a point in R2 already. It's a different point. Just now we cannot. Just now we only see this as the value you can get from 0. So you cannot get all of them. But now we treat it differently. Every point is a different point. Okay? Yeah. Okay. So how should we write this? Yeah, I think that's it. That's it I want to say about this example. Obviously, you need to check that, oh, this is continuous, blah, 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 blah. Is it continuous? Hash is a homeomorphism, right? And then projection is continuous, so very continuous. But we got a hack here. This hack is the compactification, the embedding, huh? Yeah, so you see, you see 这个 proof 重不重要哈？这个 proof 到底重不重要？这 proof 很重要诶。你要为什么这个 hash 是一个 homeomorphism 很重要。This general proof is very important to give you this hash to be a homeomorphism. Okay. Yeah. So that you don't need to worry about, oh, why this hash is a homeomorphism. Then you can prove it in general. Okay. So another what? Another reason why we look at this example is, you see, this function, this compactification, how do you obtain it? Actually, we are using the graph of this function on the space we want to compactify. So this is the idea behind Stone-Check compactification. We want to compactify our space such that all the continuous function on this space can be extended. We just extend one of it right here. I want to put more. All the continuous function that I can define on 0, 1, I want to extend all of them. I want the space to be able to extend all of them. Then this is what we call a Stone-Check compactification. Okay, so that's why we call it a maximal compactification. Why is it maximal 呢？我全部 continuous function 都可以 extend 出来，在这个 space 上面。Okay, make sense? 对吗？前面 if you look at the previous example, we are sort of extending the graph actually. Inclusion and then parameterization right. Okay, we are actually kind of completing this graph. Okay, so now we're gonna define this. Yeah. Okay. Okay. Wait, let me see how long we can go. Maybe we won't have time to do proof, but okay, in that case, let's write you the definition since we already mentioned about it. So the Stone-Check compactification, we call it a BX, beta X. Actually, we only define on a completely regular space. So later, maybe when you expand, when do we get this kind of completely regular space? So we only define Stone-Check compactification on completely regular space. This is the only place we can do this. It's actually a compactification of X. Compactification of X having the property that every bounded continuous map, okay, F from X to R, not just extended, could be extended uniquely, okay, to a continuous map of Y into R. Okay, so this is a stone check compactification. So why we care about completely regular? If time permits tomorrow, then we will prove that topological space has a compactification Y that has this property. Every bounded continuous map that can be extended to a unique continuous map if and only if it is completely regular. Okay, completely regular means what? 2 points or 2 closed set can be separate. 2 closed set. 2 closed set can be separated by a function. Anyone still remember what's completely regular mean? I remember completely regular imply regular. What's completely regular? Something separate by function, meaning you can send one set to 0, one set to 1. But the 2 set is closed set or open or 1 point. Larry. Completely regular. 3.1 is it? T 3.1. You can separate one. What can you separate? Closed set, or closed set 1 point? Can find? 有人找到吗？什么是 completely regular？ 找到吗？什么？什么？哦 set a point, close set and point. Okay, so you can separate a close set and point. So apparently, if you can separate a close set and the point, then you can extend you can have a compactification that extend every bounded continuous function. And then another corollary is a topological space is completely regular if and only if it is a subspace of a compact T2 space. T2 is what? T1 is slightly weaker than Hausdorff, right? But T2 is Hausdorff, right? Yeah, Hausdorff, okay. So if you are subspace of a compact Hausdorff space, then you are completely regular. Then if you are completely regular, you can do this compactification. Okay, so this is the story. Okay, any question? Any question before we finish? Any question? Tomorrow, I think if we got time, we'll talk about a stone check compactification of open interval 0 to 1. I think we cannot fully determine it, but we will show that it is not something that you have seen before. All right, so see you tomorrow. Okay.